have you ever stopped to think, like really think, about what happens when you hit send on an email or start streaming a movie? All that data flying across your network.
Yeah.
It's not just chaos, right? There's some incredibly clever engineering going on underneath. Today, we're diving into the real building blocks, the Ethernet frame, and a fascinating little piece inside it called EtherType. You can sort of picture it as the instruction label on every single digital package flying around.
Exactly. And our goal today really is to give you a bit of a shortcut. We want to help you understand how these basic things not only carry your data, but also how they manage all the different types of traffic at once, and even how devices find each other automatically. We'll look at some of the history, the smart ways they solved early problems, and why these details, which might seem tiny, are actually fundamental to, well, pretty much everything you do online.
Okay, cool. And to help us unpack all this, we've looked at a few key sources. We've got the Wikipedia pages for EtherType and Ethernet frame, good starting points, and also the foundational document RFC 826, which introduced the Address Resolution Protocol, or ARP. We've basically pulled out the important bits from these to piece together the story. So let's start with that Ethernet frame. You can imagine your network like maybe a high-speed delivery service. Your data doesn't just wander off, it gets packaged up properly. And that package is the Ethernet frame.
Right, and it's a very specific package format. But even before you get to the frame itself, at the physical layer, there's some prep work. You have something called a preamble and a start frame delimiter, the SFD. Now, these aren't technically part of the frame that your computer software looks at, but they're essential. The preamble is like a timing signal, alternating ones and zeros so the receiver can lock onto the signal speed. Then the SFD is a specific pattern, 10101011, that basically shouts, okay, the actual frame starts right now. Your network card, the NIC, strips these off before passing the frame up, but without them, the receiver wouldn't even know where the frame begins.
Ah, okay, so it's like the ready, set, go before the actual data packet. Once we get past that go signal, what's inside the frame itself, the part the NIC actually cares about?
Okay, so the frame proper starts with the header. First up, destination and source MAC addresses. These are 6 bytes each, a byte being 8 bits, sometimes called an octet in networking. Think of these MAC addresses as the unique serial numbers for network hardware, like burned into the network card itself. There are the to and from addresses for the local journey. Then comes the bit we're really focusing on today, the EtherType field. It's 2 bytes long, or sometimes it might represent the length of the data. You'll get into that. After that, you have the payload. That's your actual data, your email, the video chunk, whatever. And finally, there's a frame check sequence, or FCS. It's a 4-byte check, a CRC, basically to make sure the frame didn't get garbled in transit.
Okay, got it. Addresses, this EtherType thing, the data, and the checksum. And you mentioned something about a gap after the frame, too.
Yeah, that's the interpacket gap, or IPG, also a physical layer thing. It's basically 12 bytes worth of idle time on the wire. Just a brief pause to make sure receivers can clearly distinguish one frame from the next.
Right, makes sense.
So let's zoom in on that EtherType field. It's tiny, just 2 bytes, 16 bits, so you said it's crucial. Why? What's its main job?
Its main job is to act as a signpost, a protocol identifier. It tells the receiving machine what kind of data is inside the payload. Is this payload an IPv4 packet, which is, most internet traffic today? Is it an IPv6 packet? Is it an ARP message, which we'll discuss later? Without that EtherType field, the receiving computer gets this bundle of data and has no idea how to interpret it. It wouldn't know which software module should handle it. It's like getting a package with no label saying what's inside or who it's for protocol-wise.
So it's the thing that says, okay, this is internet data handed off to the IP stack, or this is an ARP request. The ARP module needs to see this. But you hinted earlier, it wasn't always that straightforward. There was some kind of conflict. Ah, yes. History time. This is where it gets interesting. The early, very common Ethernet framing standard, called Ethernet 2-byte, used those 2 bytes only as an EtherType. Simple enough. But then the official IE 802.3 standard came along, and it decided to use that exact same 2-byte field to indicate the length of the data payload in bytes.
Oh.
So now you have a problem, right? And if a device sees a value in that field, say 500, is that EtherType 500, or is it a frame with 500 bytes of data?
Oh, wow. Yeah, that sounds like a recipe for total confusion if you had both kinds of devices on the same network wire. How did they fix that?
It definitely needed fixing. The solution came with an update, IEE 802.3x back in 1997. They came up with a really elegant compromise based on a magic number. The rule is, if the value in that 2-byte field is 1536, which is 0 by 0600 in hex, or higher, it's definitely an EtherType. If the value is 1500 or lower, it's definitely a length field. Why 1500? because that's the maximum size of the data payload in a standard 802.3 frame. The values in between, 1501 to 1535, are just undefined, left as a buffer zone. This clever trick basically allows both Ethernet the second frames, using ethertype, and original 802.3 frames, using length, to live happily together on the same network. Problem solved.
That is clever, just using the number range itself to distinguish the meaning. So ethertype essentially flags what's coming next, protocol-wise. And that must have paved the way for more complex stuff beyond just basic IP traffic.
Oh, absolutely. Once you have that reliable way to identify protocols, you can layer more features on top. A great example is VLAN tagging.
Right, VLANs, virtual local area networks, used all the time in businesses to segment networks without needing separate physical switches everywhere. How does ethertype help there?
So there's a specific ethertype value, 0 by 8100. When a receiving device sees this ethertype, it knows, okay, what follows isn't the final payload yet. It's an IE 802.1Q VLAN tag. That tag then contains the VLAN ID, priority information, stuff like that. And here's the really neat part. After that 4-byte VLAN tag, you find another 2-byte field containing the original ethertype for the actual payload. So it's like nested labeling. The outer 0 by 8100 says this is VLAN tagged, and inner ethertype then says, and the data inside is, for example, IPv4 0 by 0800.
Wow, okay. A tag within a tag, essentially. Very efficient. What about those really big frames people sometimes talk about, jumbo frames? How do they fit in? Their payloads must be way bigger than 1,500 bytes.
Yeah, jumbo frames, typically around 9,000 bytes.
Yeah.
They definitely break that 1,500 byte length limit, and their size does clash with the range normally used for ether types. There was actually a proposal to use a specific ether type value, 0 by 802.870, specifically to signal this frame is using a length field even though it's in the ether type range because it's a jumbo frame. But that proposal never actually got formally adopted by the IE 802.3 committee. So officially, it's a defunct standard.
So no official ethertype for jumbo frame lengths. How do they work then? Or did that idea just vanish?
Well, officially, it vanished from the standard. But in a funny twist, some network vendors, Cisco is mentioned in the sources, actually did implement that 0 by 870 ether type for some of their own internal protocol uses, like for padding certain routing packets. So it kind of lives on in specific implementations, even if it's not a universal standard. A bit of pragmatism versus strict standards. And it's worth remembering, while Ethernet the second framing with ethertype is dominant on Ethernet itself, the idea of identifying protocols this way extends elsewhere. Other network types, like Old Coke and Ring or FDDI, use a similar concept, often involving something called a SNAP header on top of an 802.2 LLC header to carry that ethertype information.
Interesting how these ideas persist and adapt. Okay, you mentioned the IEE assigns these ether-type values, like official badges. Could you give us a few more examples just to get a feel for the variety of things these little numbers identify?
Sure. It really shows the diversity of network traffic. We've mentioned the big ones. 0 by 0800 for IPv4. That's probably the most common one you'd see. 0 by 86DD for IPv6, the newer Internet Protocol version. 0 by 088 or 6 for ARP, the Address Resolution Protocol. We definitely need to talk more about that one. Then you have 0 by 8100, which we just discussed for VLAN tags, but there are loads more. 0 by 88CC is for LLDP, Link Layer Discovery Protocol, used by network devices to advertise their capabilities. 0 by 0842 is for Wake on LAN. Yeah, literally waking up a sleeping computer over the network. And things like 0 by 88847 and 0 by 8848 are used for MPLS, which is common in big service provider networks. It's a huge list maintained by the IE Registration Authority, showing just how much different stuff can be happening on one wire.
Wake on LAN has its own ether type. That's kind of cool. Okay, let's circle back to 0 by 06 ARP, the Address Resolution Protocol. The sources, especially that old RFC 826 from 1982, highlight it as solving a really fundamental networking problem. What was the issue?
Right, ARP tackles a core challenge. Think about it. You have protocols like IP that use logical addresses, like your IP address, say 192.168.111. That tells you who a device is on the broader network. But the Ethernet hardware, the network card itself, needs a physical address to actually send a frame on the local wire. That's the 48-bit MANC address, like 00.1A.2B.3C.40E.5E. The problem is these two address types, logical IP and physical NAMD, are different formats, different lengths. And there's no built-in automatic way to know which MASC address corresponds to a given IP address on your local network segment. You need a way to discover that mapping.
Ah, okay. So my computer knows it wants to send data to, say, 192.168.1.1, the router. But the Ethernet card needs the router's specific MAC address to actually put the frame on the wire correctly. How does it find that MAC address if it doesn't know it already?
That's exactly what ARP is for. It provides a standard way to dynamically ask who on this local network has this IP address and what is your MC address.
Hmm.
And yes, ARP packets themselves are identified by that specific ether type 0x00806, so network devices know how to process them.
Okay, so how does that request actually work? Does my computer just broadcast the question?
Pretty much, yeah. Let's say your machine X wants to send something to machine Y on the same local network. X knows Y's IP address, but not its MAC address. First, X checks his own little ARP cache, a table of recent mappings it remembers. If Y's IP isn't there, X puts the IP packet on hold for a moment and constructs an ARP request packet. This packet basically says, my hardware address is EAX, my IP address is IPAX. I'm looking for the hardware address associated with IP address IPAY. It puts IPAY in the target protocol address field, but leaves the target hardware address field empty because that's the answer it wants. And then, yes, it broadcasts this ARP request packet to everyone on the local network segment using the broadcast MC address, FFFFFFFFFF.
So it's literally shouting into the void, hey, who has 192.168.1.1? Tell me your MAC address.
Exactly. Now, every device on the network sees this broadcast. Most ignore it because the target IP address isn't theirs. But when machine Y receives it, it sees its own IP address in the target field. Bingo. Now, here's a clever bit from the RSC. Before Y even processes the request as a request, it looks at the sender's information in the packet, EAX and IPX. It adds or updates this mapping in its own ARP table. The logic is if X is talking to Y, Y will probably need to talk back to X soon. So might as well learn X's address now. It saves a future ARP request.
That's efficient. Cache the asker's details automatically. Okay, so Y has learned X's address. What does it do about the request itself?
Since it was a request, ROP-R1, and Y is the target, Y now creates an ARP reply packet, RPlayArs2. It basically fills in the missing piece. It takes the original request, swaps the sender and target fields. So now the sender hardware protocol addresses are Y's, EAY, IPAY, and the target hardware protocol addresses are X's, EAX, IPAX. Crucially, it puts its own MC address, EAY, into the sender hardware address field. Then it sends this reply directly back to machine X using the MC address EAX it learned from the request. It doesn't need to broadcast the reply.
Got it. So the request is a broadcast shout, but the answer is a direct message back to the asker. Machine X gets the reply, pulls out Y's MSC address, adds the mapping IPAY to its ARP table, and now it can finally take that original IP packet it put on hold, put Y's MSC address in the Ethernet frame's destination field, and send it directly.
Precisely. The whole process is dynamic. Addresses are learned on demand when needed, rather than constantly advertising everything. This makes it way more efficient than, say, devices constantly broadcasting their mappings just in case someone needs them. And as a side benefit, network monitoring tools can listen to ARP traffic to get a sense of who is talking to whom on the local network, which is useful for troubleshooting.
That makes a lot of sense. It's a really neat, self-organizing system built on that simple request-reply mechanism.
And understanding this stuff even helps explain some other network details. Like, why is there a minimum Ethernet frame size? You need at least 46 bytes of payload, or 42 if you have a VLAN tag. If your actual data is less than that, padding gets added. This brings the total frame size, header, payload, FCS, up to at least 64 bytes. This minimum size was important for older Ethernet systems using collision detection. A frame had to be long enough for the sender to still be transmitting when the signal reached the far end and potentially collided and bounced back. Frames smaller than 64 bytes are called runt frames and usually mean something's wrong, like a collision or bad hardware.
Okay, so even tiny messages get padded out to ensure the system works reliably. Good to know. And all these headers, preambles, gaps, they must add up, right? How much does it affect the actual speed we get?
It does have an impact, yeah. It's the overhead. If you calculate the ratio of payload size to the total size transmitted on the wire, including preamble, SFD, header, FCS, and the interpacket gap. For a maximum size standard Ethernet frame without VLAN tags, the efficiency is around 97.5%. With the VLAN tag added, it drops just slightly to about 97.3%. So you're not quite getting the full advertised speed for your actual data, but that overhead is essential for making it all work.
A small price to pay for organization and reliability. Okay, one last thing from the sources, particularly RFC 826. It mentions this idea of ARP tables being dynamic, but what happens if information gets old? Like if a device changes its MAC address or moves?
That's a really important practical point. The original ARP RFC acknowledges this, but doesn't strictly define an aging mechanism. It calls it a related issue. The protocol does specify that if a machine receives an ARP packet, request or reply, and it already has an entry for the sender's IP address, the new hardware address in the packet should overwrite the old one in the cache. This helps automatically correct the cache if a machine gets a new network card or if someone's ARP table entry was somehow wrong. But beyond that, how long should an entry stay in the cache if you don't hear from that IP address again? That's usually handled by the operating system. Most systems implement timeouts, maybe entries expire after a few minutes unless refreshed. Too short, and you're doing ARP lookups constantly. Too long, and you risk having stale, incorrect information if a device leaves the network silently. So managing those cache timeouts is part of tuning network performance and reliability.
Right, finding that balance. Okay, this has been a fascinating dive into the real nuts and bolts. We started with the Ethernet frame, that basic digital container. We saw how EtherType acts as that vital label, telling devices what's inside, and even enabling things like VLANs. And then we unpacked ARP using its own EtherType to see how devices cleverly discover each other's physical addresses on the local network using that broadcast request and direct reply system.
Yeah, and hopefully now you have a much clearer picture of those invisible conversations happening nonstop on your network. Every single thing you do online, emails, browsing, streaming, it all relies on this incredibly well-defined system. The careful packaging in frames, the precise labeling with EtherType, and the dynamic address finding with ARP. It's not magic, it's just really, really smart engineering that makes our connected world possible.
So next time things feel a bit slow online, or you just plug in a new device and it works, maybe spare a thought for that little 2-byte EtherType field and the whole ARP dance going on behind the scenes. It makes you wonder, doesn't it? What other hidden codes or identifiers are working away in the background of all the tech we use, just making sure everything connects seamlessly?